All right, welcome to the 2-6 notes. This section of notes won't be long, but you should have a lot of questions after this. This is the first thing that we've really talked about that's totally new. And while it's been alluded to maybe in Algebra 1 and we can link some parts of it to geometry, this is totally new stuff. So we're going to talk today about families of functions. What we need to understand here is there are a couple things. We're going to talk about transformations. It's the same idea of transformations that you do from geometry, except instead of moving shapes or triangles or things like that, we're going to work with graphs and functions. We're going to start with the parent function, this idea of a parent linear function, a parent function right here. It's the simplest form in a set of functions that form a family. So the linear function is y equals x. You guys should recognize y equals x as this graph, okay? This, goes through the origin and has a slope of 1. That's the parent function for all lines, okay? So we're going to look at that, and we're going to see how we can transform that into other things and other graphs too, but that's the linear one that we're going to work with a little bit today. First, just to get a grasp on it, there are two kinds of translations. Now in geometry we talked about translations, and those were when we moved or shifted something, and it's the same thing here. If we add something to the function, if we add a positive constant, that shifts it up. If we add a negative, and you see the plus k. If we subtract a constant from the function, it shifts it down. Here, if we subtract from the inputs, okay, from the actual inputs, that's why it's inside the parentheses. If we subtract, it goes to the right, and if we add, it goes to the left. Okay, so that's a translation. So let's see what that looks like with a problem. So how are the functions y equals x and y equals x minus 2 related, and then how are their graphs related? All right, well, how they're related, we can look at a table and we can look at a graph. Let's look at the table. If we look at the table, each output for y equals x minus 2 is exactly 2 less than y equals x. So very self-explanatory because we subtracted 2 from it. It's exactly 2 less every time. You see, that's 2 less, that's 2 less, it's the same thing every time. All right, so then part B, and so that's easy, okay? That's easy. And the graph is the exact same. It's just been shifted down. Every single point is down exactly 2 units, okay? Let's take a look at another example. What is the graph of y equals x squared minus 1 translated up 5 units? What does the graph look like? Well, we just take the regular table of values, and we're going to shift it up 5 units. Shifting it up 5 from minus 1 is how we get plus 4, because negative 1 plus 5 is 4. And so for every x, we add 5 to the y, and it literally just takes the whole parabola, the quadratic function in this case, and shifts it up 5, okay? So let's take a look here. How are the functions y equals 2x and y equals 2x minus 3 related? Well, how are they related? If you make a table of values, what you'll find is for every x, 1, if x is 1, y is 2. If x is 2, y is 4. If x is 3, then y is 6. For every one of those, if we do that and then subtract 3, each output is exactly 3 less than it was before. Okay, and how would the graph be related? Hopefully, what you're thinking is that it's the same thing. It's just that y equals 2x has been shifted down 3 units, and that's how we get y equals 2x minus 3. What is the graph of y equals 3x plus 3, y equals 3x, translated up 2 units? Well, if we want to translate it up, we just add 2. So it would be y equals 3x plus 2. Pretty easy stuff, okay? Now, here we're looking at a graph of an airplane altitude over a trip, and they're supposed to depart at noon, and if the plane leaves 2 hours late, well, if it leaves 2 hours late, it's going to end up being over here. And when we shift to the right, we subtract, okay? So instead of leaving at noon, it left at 2, so the function is now f of x minus 2. When we subtract, it shifts right, okay? Now, suppose the flight leaves 30 minutes early. Okay, so 30 minutes early. So if this is 2 hours late, goes to the right, then 30 minutes early should go to the left. Well, if we subtract to go to the right, then we add to go to the left. And if it's 1 hour, if the units are hours, then 30 minutes would be 1/2. So that would be f of x plus 2. That's what the function would be to represent that transformation. If you're worried about how am I going to remember what does what, there's a really good graphic organizer that I'm going to show you at the end that you can copy down to help you keep all your functions straight, all the transformations of them. So now we have a reflection. A reflection, we do these also in geometry. It's just a mirror image, okay? It's a mirror image. This, say this is our original image. We can reflect it on the y-axis, and it looks exactly the same. It has symmetry there. Or we can reflect it in the x-axis. The important part is down here. For each function f of x, a reflection in the y-axis, we make the x negative, okay? We make the input negative, okay? To reflect it in the x-axis, we make the whole thing negative, okay? So slight difference there. And if you look at the drawing, or look at the pictures here, that should make sense. We reflected this in the y-axis, so instead it's still up 1, so the y is the same. It's the x that becomes negative, okay? If you look down here, it went down 1, okay? Still, the x is the same, but the y is negative, so we go down 1. All right, so let's look at some problems here. So if we were to reflect a function algebraically, so g of x, we're going to try and get g of x and say that that's the reflection of this function here. What is the function rule for g of x? Well, for a reflection in the y-axis, we change the sign of x. So g of x is now equal to f of negative x. All right? Evaluate f of negative x. Well, we did this recently where we took values from a function, we plugged it into the original and got a new function. So that's what we do. We take this negative x, we plug it into the original function right there, and then we simplify. 3 times negative x is negative 3x. And so we end up with this g of x that's going down like this, and if you look at it, it's an exact mirror image in the y-axis, okay, of the original function. Let's take a look at number 3. Let h of x be the reflection of f of x equals 3x plus 3 in the x-axis. What is the function rule for h of x? Well, hopefully you're thinking, well, in the x-axis it was different. We make the whole thing negative, okay? So if you make the whole thing negative, how would we rewrite this? Well, h of x is negative f of x, okay? Then that negative f of x, well, we can substitute 3x plus 3 in, I left out a 3 there, sorry about that. There we go. So it's negative 3x plus 3, and then we can distribute that negative sign to each, and we have negative 3x minus 3, okay? Easy peasy. We can also stretch things and compress them, okay? A stretch or a compression. So if we multiply all the y values of a function by the same factor greater than 1, that's how we get a stretch. If we multiply them by a value that is between 0 and 1, that's how we get a compression. So if you take a look here, the original function is the blue one, okay? Not sure if you heard the knocking. I'd like to welcome everybody to my house. You guys don't know you're here, that I'm here, or that you're here, really, because you're not here. But you don't know where I am. Welcome to my humble abode. Take a look around. It's nice, right? If you do know where I am right now, that's weird, and you should stop following me. Okay, so the blue one is the original, right? So if we multiply the original by a number greater than 1, it stretches it. It gets bigger like that. If we multiply the blue one by a number between 0 and 1, it squishes it down and sort of compresses it. Sort of the same curve, but just been squished. Squished is a technical term. Okay, so take a look at the table at the right. And it says, what are corresponding values of g of x and possible graphs for the transformation g of x equals 3 times f of x? So we literally take the function that we have, okay, and then for every f of x, we're going to stretch it by 3. And we do that by multiplying. So instead of 2, we have 6. Instead of 2, 6, negative 3, negative 9, you get the point. And then that becomes our new function. That's the function g of x. The question down here 4a says, for the function f of x, what if we were to change it to, for h of x, what if it was 1/3? So now we're going to compress it. Okay, so take a look here. I'm going to start just a new column right here. I'm going to answer this right here. H of x. So now I'm going to take the original and multiply it by 1/3. So that's 2/3. 2/3, negative 1, 1/3, and negative 2/3. If you're not sure how I'm getting these numbers, I'm multiplying each of these by the 1/3. Okay, I'm multiplying each of those terms by 1/3. All right. The part B says, if several transformations are applied to a graph, will changing the order of transformations change the resulting graph? And the answer to that is kind of complicated, because the answer is sometimes. It depends on what transformations we're talking about. If we're talking about two translations, probably not. It's just going to move it here and then move it there. But if we're talking about compression and stretching, then it could. So it depends on the order a little bit, and it's a sometimes answer. Here's the graphic organizer that I was telling you guys about. I think this is hugely valuable. I would copy all this down so that I had a good idea of what was what. All right. Vertical translations, anytime this is greater than 0, this right here is greater than 0, it's going to go up. And this is less than 0, it's going to go down. Right here, translated to the right, h units. That's how we get to move to the right when we subtract. Subtract goes with right. And then if we want to move it to the left, we add inside. Okay. Here, a vertical stretch. If this is greater than 1, it's a vertical stretch. If this is between 0 and 1, it is a vertical compression. And then for reflections, out front would reflect it in the x-axis, and inside that reflects it in the y. Sometimes, if you needed to pause it, here, I'll go back. There, pause. Write down what you need. Unpause. Off we go. Sometimes we have multiple transformations at the same time. So here, for example, the graph of g of x is the graph of f of x equals 4 compressed vertically by the factor of 1/2 and then reflected in the y-axis. So they want us to take this, compress it by 1/2, and reflect it in the y-axis. So we do them one at a time. The compression, that's 1/2 times 4x. That's how we got 2x. And then reflection in the y-axis, we make this negative, and we end up with this. And so the new function rule for g of x is right here. Okay. Then we have to be able to do the same thing backwards. Okay, so I'm going to tell you, here's f of x and here's g of x, and you tell me what transformations happened, specifically what happened. And to get from 2 of x squared to 6x squared, we multiply that by 3, and then the minus 1, we just subtracted 1. So what two transformations are those? Well, what we did was we stretched it vertically by 3 and translated it down. Okay, no problemo. Let's take a look at the examples. Why don't you go ahead and pause the video here. Try these on your own. Please, pause the video. Try these on your own. Okay, go now. Go. Pause. Pause. All right, welcome back. 5a says the graph of g of x is the graph of f of x equals x, stretched vertically by a factor of 2 and then translated down. So that is g of x equals 2x minus 3. The 2 stretches it vertically, and the minus 3 translates it down. Okay, no problem there. Then we're asking what transformations change the graph f of x equals x squared to the graph g of x equals the quantity of x plus 4 squared minus 2. Okay, we see a plus inside, so I know that's a move to the left, and this is a shift down, so hopefully you got it's been translated left 4 units and translated down 2 units. That's it for the notes, guys. You should have questions. You should come to class ready with questions on how to do this stuff and how to know when to do what. Without the questions, I got nothing for you. Oh, that's not true. I got 2 questions for you. 1, how many seconds were left on the clock when Sam supposedly made a basket on me during the intro music? Also, how did he spell girl? Just curious to see if you picked up on that. See you in class. Bye.